Okay, PF1 video 7. So we started from scratch then in the last lesson and wrote a couple of programs that didn't do a whole heck of a lot, but we just experimented with a little minimal program. Hey, we wrote a famous program, I guess, Hello World, and then played around with printline. And, oh yes, then also started talking about data types, and we're going to jump into that then. We're going to kind of just follow up with that. So we introduced the concepts of bits and bytes and how many discrete values could be represented with integer types of different types. And so we're going to just kind of continue to add to that then. So let me pull up my notes. You guys do the same. All right. So we will start here and here and here. All right. Down to the bottom we go for vid7. Alrighty. All right, let's talk about our data types for Java. Java data types that we can use to declare variables. And we're going to start off with the simple data types. All right, simple data types. All right. So, and these are all, these data types, they're all reserved words in Java. And hey, we need to cover this at some point. So now's as good a time as any, I guess, talk about Java reserved words. And so let's do a quick Google. And it always takes me a minute to find a good list that I'm happy with, but Java reserved words. They are words that mean something to the Java programming language. And since they have meaning to the language, Java doesn't want you using those same words for other things, such as the variable names or method names or class names and so on. So I'd like to see just a list. I don't want it to define all of the keywords, which is probably what many of these are going to, like this. That's not what I'm looking for. I just want just a list. Just the list. We'll just keep clicking here. Hey, there we go. Hey, that looks like a web page I could have made. That's a really exciting web page. Black text on a white background. But anyway, there's our Java reserved words. So we have 1, 2, 3, 4, 5 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like, so anyway, 50. Looks like maybe 50 reserved words. Anyway, and a bunch of them are the data types that we're going to cover. I'll just minimize this and leave it here. We'll kind of refer back to it in a bit. But anyway, the simple data types, they're all reserved words. And the simple data types, you're not going to be any surprise to you at all, but let's go and just put them into our notes here. All right, so how about we'll start off with the integer types. All right, so the integers, well, we have the little guy, how about byte, all right, which is 8 bits. And then the range of values for that, we talked about this last time. A total of 2 to the 8th is 256, so there's 256 values. And unfortunately, I wish they gave us an option in Java, but they don't. Maybe those 256 values, they kind of straddle the origin there in the number line. And so we have 127 of them that are negative, 128 of them that are negative, and 128 that are non-negative. So anyway, the range runs from negative 128. And then through the origin, and that one counts, and then anyway, because the origin counts also, we tap out at 127 then on the positive side. So that's not the biggest integer there. To be able to store an 8-bit integer, you tap out, you max out at 127. So a little bigger than a byte would be a short. All right, and what the heck, I'm going to give plenty of space for these. The short's going to be 16 bits, or in other words, 2 bytes. And we mentioned that last time, and I'm not going to worry about writing the exact values down, but you remember that, oh yes, when the game consoles and computers jumped to 16 bits, then we had 64K that we could address. All right, so 64K. And all right, so that would be starting at 0 and going up to 64K, which is 65,538, I think it is. Anyway, of that 64K, well, half of it is negative and half of it is non-negative. So I'm going to say, well, we'll just be a little lazy here. So from negative 32K to positive 32K. Now, I guess, if we define K as 1,024, if I put a -1 on there, then that would be perfectly fine. But, I'm not going to worry about that level of detail. So we got roughly we can even just say roughly 32,000 that are negative and 32,000 that are positive. It's a little more than that because a K is a bit more than 1,000. A K is 1,024. All right, and then again, we're going to double every time. So we go from a byte to 2 bytes, which gives us a short, to 4 bytes, which gives us, the good old int. The good old int. So 32 bits, say we're getting somewhere with 32 bits, of course. That gives us 4 gig, or in other words, 4.3 billion. And well, of the 4.3 billion, half of it's positive, half of it is negative. So we'll say from, approximately, negative 2.1 billion to positive 2.1 billion. These are a little bit of an approximation, but anyway. All right, so that's pretty darn big. And then the big boy, the long, which is going to be 4 bytes or 64 bits. And we talked about that last time. Then you get 18 quintillion. So how about from negative 9 quintillion to positive 9 quintillion? If that number means a whole lot to you, there probably doesn't to any of us. Again, that's getting to be a pretty big one out there. So those are our integer types. Those are our integer types. And we're going to do some experimenting around with these things here. We're going to play around with these, and we're going to find that one of these is our favorite, if you will. So I'll just leave that later. We'll come back and put a star by it that's our favorite of the integer types for reasons that will be clear soon. And this is kind of a cousin of the integers, if you will, for reasons that will be clear at the end of PF2, believe it or not. But anyway, how they're represented and some details on that and so on, we're going to talk in depth about in PF2. But kind of closely related to the integers, closely related to one of the integers for sure, is going to be our characters. All right, so our character data types, characters, if you will, or character data, and the data type, I could, just for the heck of it, I might do a bold here and a bold here. These are the Java reserved words, byte, short, int, long, and they are all, quote, integers. They're all integer types. And then for character data, we have a type here. And anyway, we'll do the old bold here again. So how about char? Just how that is. We often pronounce it as char. And all right, and you can store a char at just 8 bits or 1 byte. We'll just say 1 byte. All right, for that. And all right, what else? Oh yeah, another kind of a funny one here. To store true, false, yes, no, on, off kind of data. In fact, we'll just even write it that way. Yes, no, or on, off, or true, false, to store information that is of that type, we would use a Java simple data type called a Boolean. We'll bold that also, Boolean. And well, the truth is, a Boolean, just like think about our little discussion with a view of the business building from the park and so on, just a single window either being on or off. In other words, that represents a single bit. That's all you need. All you need is a single bit to store the answer to a yes-no question or an on-off question or a true-false question and so on. So ultimately, all that a Boolean really needs is 1 bit. 1 bit. But if you remember, the smallest addressable unit of memory is a byte. So bytes have addresses, and of course a character would have an address also because it sits in a single byte. But anyway, so 1 bit, that's just a tiny little fraction of a byte, it doesn't have an address on its own. So you're going to have to allocate a byte, even if ultimately all that you really need is a Boolean variable. The good news is, if you want, and I'm not sure how much of Java will do this for you automatically, in C and C++ we have greater options available to you and so on. You can actually cram 8 Boolean variables into a single byte through something called bit masking. It allows you to access this bit of this byte or the other bit of this byte and so on. So you can be very efficient on your utilization there of space by doing the bit masking. Let's see. Oh yes, and oh gosh, yeah, this is perfectly fine in terms of the order. So how about now the floating point? Floating, quote, floating point. In other words, numbers that have a decimal point. All right, so we've got 2 of those. The smaller one is called float, and it is going to be a 32-bit. Oops, don't need bold on that. Or in other words, 4 bytes. And then we also have, bold here, double. Double, there was that. Which is the big boy, and that is 64-bit. Okay. So, all right, so there are those, and those are the simple data types. All right, so let's see, lining up here and tabbing over here. And, all right, so I'm kind of lined up vertically underneath the simple data types. So all of these were simple data types. I could put a box around those or something, but I don't want to get too fancy, I guess. Those are simple data types. But now I'm going to come down here, and we're going to then introduce a data type which is not a simple data type. All right, so this is going to be, either we call them classes or objects. All right, and down under here, string data is going to be stored in a data type, and I'll bold that so all of the bold information here are the data types, and it is called string with a capital S. All right, and the sizes vary, if you will, depending on how many characters are inside the string. Oh, I don't need to bold that. So I'll let you guys catch up with me here on your typing. So anyway, do note that all of the boldface words there are data types that are available to us in Java. All of them except for string are simple data types. They're also called primitive data types, would be another term. And they're all built into the language. And again, these simple data types are kind of more fundamental, and ultimately they're faster and easier to access and so on. They have some advantages. String is very flexible, but it's a little more involved. It takes a little more memory. It might be a little slower to store information in a string and so on. But anyway, so we'll talk about these in greater detail. And if I move this over here to the side, and then I pull up our web page here again, did they really need to put this much vertical space in there? It's really kind of bigger. Okay, there we go. That's good. So check this out. So here's our list of, I think it was 50 reserved words. And so notice they're in alphabetical order. Oh, here's byte. Okay. And here's char. And here's int. And here's double. And here's float. Anyway, so the primitive data types are all reserved words. Looking over here with the S's, static, strict. What the heck? Why isn't string there? Well, again, that kind of just reinforces there's something different about string. All of the simple data types, all of these first 4, 5, 6, 7, 8, all these first 8 data types here, the simple data types, also called primitive data types, they're kind of built into the language at a lower level, if you will. And in fact, all of these things, byte, short, int, long, those are all reserved words. All right. But string, on the other hand, well, no, it's different. For now, just remember that's different. It will all become clear as we go through this semester and the next one then. All right. So there's our data types. So we're going to start declaring variables here pretty quick. But back to our notes we go. And all right, we need to give you the rules on naming variables and naming methods and classes. And you remember already that we have written programs, a number of different classes. We had a class called Lab1. We had a class called vid7 and vid6b then on the last class period. And so anyway, we've named a number of classes. So far, we've only written one method, one little method. And all of the programs we've written, every program has had one method. What was that method called? Everyone's going to do the old palm to forehead when we tell you. That one method was called main. You remember that? Execution starts at main. Remember the first program we wrote in the last lesson, we created a class, it compiled, but it wouldn't run, and we tried to run it, it says can't find the main method. So we put it in our notes, execution starts at main, and it wasn't that our pro tip? Yeah, there we go, execution starts at main. So of all of the programs we've written, we've had a number of different class names. And anyway, each one of those programs had a method called main. But you can have other methods. We'll get there ultimately. Anyway, so in order to name variables and methods and classes, we need to know the rules that govern that, if you will. So we're going to do that here then. And we're going to show you the identifier naming rules. Identifier naming rules. And in parentheses, an identifier... You're wondering, this is the question that was on the tip of your tongue, I'm sure, is the name of a variable, method, or class. So the same set of rules apply when we're coming up with a variable name or a method name or a class name. So let's jump into those, and then we're going to start writing code as we go. All right, so rule number 1. All right, so identifiers are going to consist of letters, characters, the underscore, and the dollar sign and the underscore, as such. Okay. So the comma is just a separator there, to be clear. Letters, comma, characters, comma, the $, comma, or the underscore. To be clear, a comma cannot appear in a variable name or a method name or a class name. I think it's time we jump over here then. Letters, characters. Oh, you know what? Now that I say that's actually redundant. Letters, characters. Let's say letters or numbers. Yeah, duh. Numbers. I apologize for that. Letters, numbers. Yeah, that's good. And now let's jump over and let's start writing a program. I need to do a little house cleaning. Remove. All right. I'm going to get rid of our vid everything from last class period. This looks pretty good. I have one other extra Java file there, but that's for PF2. I'm going to leave that there. So vi vid7.java. How about public class vid7 with an open and a close? And then inside of that, all right, indented over by 4 spaces. All right, public, static, void, main, all lowercase, open parentheses, string with a capital S, args, open, close, square bracket, close parentheses, and then more spaces, and open and close curly braces. So there we go. That should be just a little starting point, kind of the smallest little program that will compile, run, and do nothing at all. Interesting, doesn't generate any output or anything. In fact, gosh, we're not going to get much output of anything that we do here today, but perhaps a little bit. All right, so letters, numbers, the $, and the underscore. So let's experiment with that. And all right. So, the number one most popular data type of all programs ever written has got to be the good old int data type. So, it's just used all the time for reasons that will become clear the more we do in programming. So I'll just stick with that, I guess. The first variables I'll declare are just going to be integers. And of the integer types, I mentioned we're going to have our favorite, and we'll kind of show you why here in a little bit. But for right now, we're just going to use the default, which is just int. And let's come up with some variable names and see if they work or not based on what we learned in our very first of the identifier naming rules. So letters, in other words, letters of the alphabet. So how about, A, B, C, 1, 2, 3, and the $, and the underscore, and slap a semicolon at the end. Oh yeah, we ought to give you the syntax for this. And, we'll do that soon, I guess. But for right now, I won't worry too much about the syntax for a variable declaration statement. But that's what this is. We are declaring a variable. It is a variable declaration statement, and statements end with a semicolon. To be clear, this isn't a statement. This is the method header. This isn't a statement. That is a class header. This is a variable declaration statement. So again, just like learning a spoken language or written language or whatever, programming languages have a syntax, have a grammar, and so on. And all right, so that consists of letters of the alphabet, some numbers, the $, and the underscore, and we believe, according to our identifier naming rules, that should work. So how about we, get our command history set up here, right? vid7.java, Java C, vid7.java, and it compiles up, so it looks good. And I'm not going to bother to run it, just because it's not going to generate any output, but it will run. It would run, we just wouldn't see any output. So that looks good. Now, all right, so are there any requirements on the sequence of those letters and numbers and special symbols? And so we'll do that next. But I'll tell you what we'll do just for the heck of it also. How about we come down here and do something similar? All right, DEF 456, and I'm going to throw in a dash, for instance. I don't know about you guys. You kind of think, hey, on the old keyboard, the underscore and the dash are the same key, and they're both kind of little short horizontal lines. What's the difference between one and the other? I bet that if an underscore works, I bet a dash will also. And one thing I certainly like about programming is when you come up with a question, will this work, or how does this work, or whatever, certainly the will this work questions are very easy to answer. You type the dadgum things in, and you compile it and see if it compiles, and run it and see if it works like you expect, and so on. The how does it work? Well, that might be take a little more study perhaps, but will this work? Any question you can ask, you can just try it out. So we'll cat and compile, or well, try to compile. Anyway, there we go. So didn't like that. It is pointing to the little dash here, and it says a semicolon is expected, which anyway. So yeah, in other words, after the variable declaration statement, we want a semicolon. So the semicolon is expected there, not the dash. And we can kind of understand, or I'll ask, why would you guess that the dash wouldn't work? Think about the arithmetic operators from your math class. What's that dash very likely going to tie into when we're putting together expressions? Subtraction, right? So that's the subtraction operator. You know, for the same reason, would you expect the plus sign to work? No, and so on. So anyway, so that didn't work. All right, so fine. So we could leave it there and comment it out just so that we have a hope of compiling again would be fine. And just for the heck of it, let's go and do another one. And I'm going to reverse the order of some of these things. All right. So how about if I say 1, 2, 3, A, B, C? All right. Just leave it at that as far as that goes. Hey, that consists of letters of the alphabet. Yep, got some of those. Numbers, we got some of those. Yeah, that looks pretty good. So let's see if that will compile. So we'll cat it for good luck. We're going to need some good luck here on this one also. We compile, or well, try to compile. And hey, here we go, one of those situations. We have one problem. It gives us 3 errors. So 3 syntax errors on one line of code. And now here it's pointing to the word int. And then here it's pointing to the space after the word int, and here it's pointing to our, quote, variable name. And now, you know, Java has good diagnostics, but sometimes the messages aren't as helpful as others. Not a statement. Well, it's not a valid variable declaration statement. It could have been more clear on that. A semicolon expected, that'd be kind of strange. A semicolon right after the word int actually by itself, that wouldn't compile either. And anyway, not a variable declaration statement. So bottom line here, it's kind of confusing. It's giving us several not especially clear error messages. But we got a problem on line 7. And oh yeah, I forgot. Rule number 2. Rule number 2. All right. The first character can't be a number. So we blew that. Okay. And can it be, does that mean it can be a $sign or an underscore? Well, let's try that out. So we'll go in here and all right, so we'll comment that out. I may end up eventually removing these or not. We'll see here. But how about int and underscore? And then we'll say whatever, 1, 2, 3, A, B, C. Is that going to fix our previously incorrect syntax for a variable name? Just by sticking the old, I might have said underscore the $sign, by putting a $sign over an underscore, either one, in front of it. Will that fix it? In fact, what the heck? We'll do a YY and a P, and put an underscore on one, the $sign on the other. All right, cat, and compile, and it does compile. So there you go. So you can have a letter of the alphabet as the first character in a variable name, or you can have our $sign or underscore. You just can't have a number as the first character. All right, so we learned that. What next? Oh yeah, you know, the next rule, we'll go ahead and write it down, and we could put together a little test perhaps, but this kind of makes sense. Can't be a reserved word. A Java reserved word, a reserved word, either one is fine. So of course that makes sense. Those words have meaning to the language, and we're going to just try to grab hold of that and turn it into a variable that then we can make assignments to and so on. That would be pretty crazy if that did work. And we'll just verify, you know, hey, big surprise, you can't say int Boolean. Hey, I'm going to declare an integer variable, I'm going to call it Boolean. Well, Boolean is a data type, and that's accomplished by making Boolean a reserved word there. So we'll just take a look at what the error message is just for the grins, I guess. All right, try to compile that bugger up. And kind of the same as last time, isn't it? In fact, I think it's the exact same message as we got last time. Not especially descriptive. You know, it'd be nice if it said Boolean as a reserved word or something like that. But, again, has good diagnostics as far as programming languages go, but they're not always perfect. So back in we go. We'll comment that out. That violated rule number 3 there. All right. And, okay, how about, oh, yes. So here's a... Oh, in fact, we'll type this down in just a minute. I'll just ask your question. Int I and int uppercase I. So, we'll do this first. We'll do this first. I'm going to make the uppercase I lowercase. Now, would you expect this to work? Have 2 variables named I, one declared right after the other? Yeah, very, very good. That's exactly right, Caden. You know, kind of like you can, in a directory cannot contain two directory entries of the same name, because then it's arbitrary which one are you trying to refer to when you refer to it by name. If we have 2 variables called I, how in the heck do we specify which one of those I's we're trying to access? No, they have to have unique names. So that would not compile. So the bonus round, what about that? Is lowercase I going to be recognized as being different from uppercase I? And that's exactly right. I see a number of students, they're guessing yes, because we've mentioned Unix is case sensitive, programming languages tend to be case sensitive. We'll put that as a rule down here. Hey, the good news is it's not really a restriction, it's actually kind of helpful to us here. So Java is case sensitive. So it will recognize that there's a difference between lowercase I and uppercase I, and unlike before, we will, after we cat, then try to compile. It does compile. It does compile. Oh, what the heck. This is the very first time we've thrown in variable I. There will be few days over the next, as far as that goes, 3 semesters, certainly this semester or next, there'll be very few days where we write a program that does not have variable I. Variable I is the most common variable in all of programming. Variable I is almost always going to be a good old integer, very likely a 32-bit integer like we have here. So why is variable I very common? So a little bit of programming history, I guess. So when we talked about programming history, back in the 50s, there were 2 programming languages that were created that were the first high-level programming languages, the first 3rd-generation programming languages. In other words, something other than UG, machine code or assembly language. And COBOL was one. That was for a business. And then Fortran, remember that, for science and engineers. And anyway, so this is explaining why I is a very the most common variable name of all across the globe. And here's the explanation for it. 75 years ago in the early 50s when Fortran was created, again, I guess programmers are lazy and they're going to make things easy for themselves and other lazy people, And so when they created the first Fortran compiler, and they, we need to define our variables and so on. Even in assembly language, you declare your variables and reserve space for them, and you can associate a name with them and so on, But anyway, in Fortran, they decided, maybe it would be nice if we didn't have to declare our variables. Then we could just skip that step and go on. We just start using a variable. We just make an assignment to it, and we go on, even though it's never been declared. But, well, ultimately, space has to be reserved for that variable. It's either going to happen because we declare it ourselves, or there are some built-in rules to the compiler. When it sees a variable that's never been declared, it's just going to have to use some rules to determine, what do I do with this unknown variable? Do I give an error like Java might do these days, or do I go ahead and just make some assumptions about that variable, and I'm going to go ahead and allocate space for the programmer on their behalf? I'm doing them a favor, and I'm doing it instead. And that's what they did in the in the Fortran compiler all those years ago. I just need a place to doodle. I'll just come down here. So anyway, the word integer, the first 2 letters of the word integer, I-N-T-E-G-E-R. So the word integer, the first 2 letters are I and N. So 70 years ago, when they created Fortran, just so their programmers could be lazy, they decided, here's what we're going to do. If the programmer just introduces a variable out of the blue, they just start using it and it's never been declared. If the first letter of that variable name is I, J, K, L, M, or N, I through N, all right? If the first letter of the variable name is something between I and N, we're going to assume that that variable is going to be an integer, and we're going to declare an integer variable on their behalf. They won't have to do it. We'll do it for them. If it's anything else, in other words, if it is A through H or O through Z, then they were going to declare it to be a floating point variable with a decimal point and digits to the right of the decimal point and so on. Because again, back then, programs were written to do number crunching. What about character data? What about string data? That's kind of a separate thing. Early computers did a poor job of dealing with those things if they handled them at all. But those earliest programming languages were just meant to deal with numbers. And anyway, so the variable name starts with I through N. It's going to be an integer. And so, hey, the early Fortran programmers they learned that little rule, and of course, being the lazy bums that they were, they just decided, great, I'm not going to declare any integer variables anymore, and they just started using I, J, K, L as kind of their default go-to integer variable names. So they wanted to be lazy, not have to declare a variable, and they also were lazy, and they just picked, that's the variable name, I. The rule says it just starts with an I. But instead of using I whatever, they just I by itself. So it's the smallest little variable name you come up with, a single character long, and they didn't even bother to declare the darn thing. And so that just became widespread. And so Fortran programmers for decades then were just using I, J, and K as their default integer variable names. And then when they stepped up to the C programming language, for instance, then in the 60s, guess what their favorite variable names remained? I, J, K, even though they didn't have that same little handy feature anymore in C and C++ and Java and most programming languages, unless they're scripting languages these days. You have to declare your variables. But it's just funny how things get passed down from generation to generation, even within technical families or whatever we could say, I guess, So even to this day, 70 years later, the most common variable all is just I. All right, and now you know the rest of the story there for that. Okay, and all right, so that did compile. So because of case sensitive. And all right, the last one here, and I'm going to put a star by him. All right, star 5, and that is class names should start with a capital letter. Should start with a capital letter. So I put a star by it. The compiler's not going to force you to name your class names with a capital letter. We talked about that, in fact, on in the last video. If I was to come in here and change this to lowercase vid7, and then move my file, all right, Java C, vid7.java, it compiles up just fine, even though it contains a class name lowercase v for the first letter. So class names should start with an uppercase letter. Hey, this is my class name, and I was lazy and didn't make it an uppercase letter. It's still compiled, so that's more of a convention than a rule, but we shoehorned it in there with the rules anyway. So let me move that back. Move vid7.java to vid7.java. I'll remove my class files here. That'll get rid of both of them, including the lowercase vid7. And then that's right, 7.java. And come over here and change that back to an uppercase. Okay, so there's that. So there's our identifier naming rules. Let's go in our notes then also and show you the syntax for a variable declaration statement. You've seen some simple ones here, but they can get bigger and uglier than that. All right. And gosh, in this particular class I'm teaching right now, we did miss one day of class due to a snow day, and I assigned a video then. But I believe in that video that we did introduce the syntax for, syntax for Unix commands, and then also I mentioned that the same syntax could be used to express the syntax for programming language statements and so on, where we can use uppercase letters and brackets and different things. So I think this should be not completely new to you, but we'll find out here for sure, I guess. The syntax for a variable declaration statement would look like the following. We're going to have a type followed by a variable name. All right, and name. Now, if you're writing in pen, then hold off just a second here then. So just kind of stop at that point. So I'm temporarily going to, for instance, put a semicolon here. And okay, well, that's kind of the minimal variable declaration statement that, in fact, all of these variable declaration statements over here follow this particular syntax. You have a data type, which can be int, or, well, in fact, any of these data types here that we've reviewed earlier, followed by a variable name. So again, I'll just ask, since we did have that snow day this particular semester when I'm making this video. So didn't we cover this on that day? Does that sound familiar? That, oh yes, an uppercase word here, that means replace it with an actual whatever. Yeah, okay, I'm seeing a number of nods then. Like, how do you run the VI program? VI space file name, and I write that in all uppercase. Put your actual file name in place of FILENAME. Same thing here. You replace this with one of the data types. You replace this with your variable name that follows our identifier naming rules, and then, oh yeah, don't forget to put a semicolon at the end. So that would be the syntax for the absolute minimal, simplest little variable declaration statement. I'm going to take that off, the semicolon off, and then do the following. Square bracket equals init value, close square bracket. And temporarily, I'm going to put a semicolon here again, but the semicolon is going to continue to get bumped down to the right here. So if you're writing with pen, kind of lag behind me just a little bit. Okay, so our memory test then, if we've talked about this syntax before, and I think that, that's right, within Unix commands and so on, we can end up using these square brackets also. Does anybody remember what the square brackets tell us? What's in the square brackets are or is? Optional. Good job, optional, exactly right. Oh, So if you want, you can initialize. So initial value is what my little word here is kind of standing for. If you want, you can initialize that variable that you just declared. So in other words, going over here, you know, I've declared variable I, for instance, already, and then I could say I is equal to 7, you know, that would work perfectly fine. Or I could say int j equals 7, all at one time. So you can declare your variable and then assign it or initialize it separately, or you can declare it and assign it an initial value all at the same time inside your variable declaration statement. So that's kind of cool. And then back to our syntax here. All right, so get my cursor right, back over here then again. And then, all right, more stuff. Open square bracket, comma, then comma, there we go. And then var name, okay. And, all right, so there's that. That looks good. Oh, what the heck, then we'll go and finish it. And then another open square bracket equals init value, close square bracket, good heavens, dot, 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 and then another close square bracket. I think we're done. So I'll let you get that written down, then we'll talk about it. All right, see some folks kind of strain a little. I'll make that bold so it shows up a little better for you then, because the syntax of that is kind of detailed. Make sure we have square brackets paired up correctly. Uh-oh, we're missing a close. Oh, no, we're not. Okay. I thought we were missing a close on the end. But this open matches with this close. And then of what's left, we have 2 opens and 2 closes. So I think we're good. All right. So we learned that, yeah, you can just say a data type and then a variable name, and then they'll semicolon at the end. If you want, you can give it an initial value. And now here's another pair of square brackets. All of this is another pair of square brackets. And what's that telling us? Oh, if you want then, after you've declared one variable and perhaps initialized it, then if you want, you can throw in a comma, give another variable, initialize it if you want. And then the dot, dot, dot. You know, we use dot, dot, dot just in English sometimes, you know, yada, yada, yada is kind of, you know, what that means, I guess. So the dot, dot, dot says, in this syntax here, that says that you can repeat what is inside this pair of square brackets. So we can do this, over and over and over again. So you can declare one variable, initialize it if you want, put a comma, another variable, initialize it if you want, put another variable, you know, with a comma in between each one of those then. I forgot to specify that. But anyway, so let's just do something like that then. All right, so we can come over here. How about int k equals 3, comma, jkl, comma, space, m equals 99, comma, n, comma, o equals, 21, like so. So you can declare as many variables as you want, initialize them if you want, just put a comma in between each one. And we only specify the data type once. What's that mean? Well, they're all ints. So let's make sure it compiles real quick. All right, we will cat, oh, that's the wrong one, that's lowercase, vid7.java, java c vid7.java. Sweet, all right, there's that. Okay, let's go back to our notes, talk about something that's pretty similar. Let's give you the syntax for just a regular old assignment statement. So looking back at our program that we have here so far, so, well, all of these are variable declaration statements, some of which that have been commented out contain syntax errors. And this here also, to be clear, look at this line up here that's highlighted. This is a variable declaration statement. This is an assignment statement. There's no variable being declared there. It's just that we're making an assignment. This equal sign, a single equal sign, that is the assignment operator. All right, it's not the equal sign. I mean, it literally is on our keyboard. But anyway, in Java, and other programming languages, we would call this the assignment operator. Anyway, but because of the word int here, we are declaring variable j. So this is a variable declaration statement. Of course, this is a single variable declaration statement. But anyway, this is our one and only assignment statement. We are assigning a variable here. We could say we're initializing a variable here, even though it's part of a variable declaration statement. But let's give you the syntax for an assignment statement. And it's not going to be near as detailed as the other one. Syntax for All right. And what the heck, we're going to do it in bold just because it looked good last time. So we're going to specify to the left-hand side of our assignment operator, we have to have a variable. Variable is equal to, and then on the right-hand side, we're going to have either a constant, or a variable, or an expression. And then followed by a semicolon. So this little vertical bar, that is the shift of the backslash. You know, in Unix, that's the pipe, the pipe symbol there. But here we would call it OR. So in programming, this little vertical bar, one or two of them, kind of depending on the programming language we're using. But anyway, in programming languages, we talk about this vertical bar. We refer to that as the OR operator. So an assignment statement, you can assign to a variable the value of a constant, the value of a variable, or the value of an expression. But anyway, this is the assignment operator, and the variable has to be on the left. So in other words, back into our code, we go over here. All right. So we said earlier that, you know, for instance, j is equal to 2. That is an assignment statement. Now in algebra, j equals 2 and 2 equals j are the same darn thing. So how about I take one of my other variables? How about 3 is equal to k? So in algebra, it doesn't matter which side of the equality our variable is on. It just doesn't matter. Sometimes it works out that way. But in programming, it does. This is not an equality. This is an assignment statement. This is the assignment operator, and it is defined that the variable has to be on the left. So expect a syntax error there on line 22. We'll give it a try. Maybe we'll slip one past the goalie here. Let's see. We got a problem, line 22. On the left-hand side, what it's pointing at, it says unexpected type. It gives us some more data. What's required on the left-hand side of an assignment operator is a variable. What it found was a value. Again, in our notes, we assign the value of a constant or the value of a variable or the value of an expression. So, oops, it does matter in programming, even though it doesn't in algebra. So back in we go. We'll just comment that out. Okay, not too bad. All right. And we'll push on just a little further here. This example is really just playing around with the bare minimum of declaration statements. We've only used at this point integers as it. We haven't explored any other data types, just haven't done much. We just kind of checking to see syntactically what would work. And I'm going to go ahead and maybe pass on and start another example. And just to be lazy, I'm going to copy vid7.java to vid7b.java. And then I'll wait here a sec. We'll go over to vid7b. We'll put a b on the end of the class name. Don't forget that. And I'm just going to gut the entire body of the main method, and we'll start from scratch there. But at least save us typing in the new class header and the main method header and the curly braces and so on. So, oh yeah, so vi vid7b.java. All right, you guys know the drill. I'm in command mode. A capital A will put me into insert mode. At the end of that line, slap your B there. And I, out of habit, automatically hit an escape there, so I remain in command mode. And then I'm going to arrow down a few and then start my DDs. Now I can do DD to delete this line and DD to delete the last line, but if you remember, the dot repeats the last edit. The last edit was I deleted the line, so once I've done one DD, now I can just do dot, 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 dot. Or I could count some lines and say, how about 5 DD? And then, okay, it looks like I maybe got about 5 more. I'll just hit a dot again. Okay, now I've got like 3 more left, 3 DD, you know, so anyway. So there's that. All right. So let's jump into our second example then, and let's play around with some of the other data types then. So we'll get started here, then we'll take a break, then we'll come back, and this will be our last program that we'll work on for the rest of the day. So let's go ahead and declare, okay, well, I'm going to cheat and come over here. Let's go ahead and declare variables of various types here. I want to try to remember, in fact, to hit all of these before we're done today. Let's declare variables that are integers. We'll just start with the smallest one. How about byte? And, you know, I need to think up variable names. And certainly we could use I. That would be okay, but I'm going to use a more descriptive variable. Again, I, J, K, L, those are assumed to be integers because of those old guys back in the 50s, and that thing has been passed on, and it's still the case. So for byte, a good descriptive variable might be, oh, how about the first letter of byte is B? I'll just call my variable name B is a variable of type byte. And the next bigger integer is short, and we'll make that S. And then we're going to have int. Hey, here's good old I. And oh, just because I am It makes me happy to do so. I'll go and line my variables up here. And then long L. So, all right, now that is an L. You know, depending on your font, sometimes L's and 1's look an awful lot alike, you know. But anyway, just since I'm here in VI, L1, not so much. This font looks pretty good. So hopefully there won't be any question there. All right, so we've done that. And let's now just, tell you what we'll do. We'll go and throw in the other data types, and we'll need to remember to get to them and use them. And how about the cousin of the integers, char, C, and a Boolean. Now, dadgummit, I'd like to use B here, but we already have variable B. That's a byte, so how about BO? All right, so BO, poor Boolean variable there, kind of got a not so good name. And we'll throw in some floating point data, float F, and double D. All right, so there's that. And what the heck, we'll throw in a string also just to have it done. So we'll even try to compile this up. All right, so do note. Oh yeah, so I mentioned our identifier naming rules that class names should start with a capital letter. That's our identifier rule number 5. And do note, string starts with a capital letter. Oh, because yeah, string is actually the name of a class. When we create strings, what we're actually doing is we're creating objects. All right, so that shouldn't make a whole lot of sense now, but it will later. But anyway, strings are different. Strings are different. They're not, all of these are primitive data types or simple data types, but strings are different. And let's just take this, make sure it will compile, then we'll start making some assignment statements to these variables. So we'll cat vid7b.java, java c vid7b.java. Oh, right. Oh, I spoke too soon. Oh, all right. I bet someone saw this. Someone saw this. Zach, you probably saw that, didn't you? No? Okay. Well, someone did and didn't speak up. They just wanted to see me crash and burn. So rats, today's not going to be the best day here. We got a syntax error that wasn't intentional. I just overlooked. So kind of like BO, we need to do something else with S to make them different. You know, we could put S2 or something like that. Oh, what the heck? We'll just kind of stick with the convention. I'll just do ST. So it is different. Okay, we'll see here. So now we'll cat for good luck. Hopefully my luck will hold here. All right. I'm guessing we're about halfway done at this point. So it's only a 9:48, something like that, about 50 minutes in. But I'm guessing that's about halfway done. So why don't we take a break? We'll come back. We'll start beating up on these variables then. All right, we are back from our break. So let's now jump in and start making some assignments and kind of exploring around these variables. And we're going to find some little weird things, I guess, associated with the integer types, for instance, of different sizes and so on. We kind of have to learn their quirks, I guess. So let's jump in here. So vi vid7b.java. And so we've got the 4 integer variables b, s, i, and l. We can just assign all of those, and we'll start off everything we just find. So b is equal to 1, and s is equal to 2, and I is equal to 3. So we're assigning integer constants, all right, and L is equal to 4. Integer constants to each of these. Again, we would say that all of these variables are integers. They're all integers. One of them is specifically an int. You know, int has a size associated with it. Integer is the general concept, you know, like from your understanding of the integers in math classes and so on. So we're assigning each of these integer variables into the values of these integer constants. And I believe this should work just fine. So that we'll start off where everything looks kind of cool, but eventually things will get kind of weird. All right, so we'll cat here for good luck and compile. Does compile. Back and we go into VI then. So now let's do some things that may not work quite as you would expect. So how about if I come here and if I say, all right, we'll do the following. How about S gets assigned based on what is in B? Now let's just back up one thing and back up a second here real quick and kind of talk about this. You know, we wrote the code more or less from top to bottom, but to be clear, when your code is compiled, it's compiled from top to bottom. Now we did mention in a lesson or two ago that the compiler actually takes multiple passes through your code, but anyway, we can kind of just assume it's from top to bottom. Oh yeah, and that's something I had to point out. For instance, you know, so since it's top to bottom, if I was to actually declare variable b down here, well, so when we compile, then also when we execute the code, oops, I did a YY instead of a DD. I'm gonna delete it from up top. So I'm declaring variable b down below all of this code. So again, when it compiles the code, and certainly when it executes the code, when it's executing the code, well, we're not going to get to it. It's because it's not going to compile. All right, we're looking here, everything's kind of good. Hey, I'm making an assignment to a variable called b. What? I've not seen variable b before. I don't know anything about that. It's going to throw a compiler error. Okay, so you have to declare the variable, and also the declaration has to precede the use of the variable then. So if we try we'll cat for good luck, but anyway, try to compile that. It ain't going to compile. We'll get a couple of errors on that, so we need to move that declaration statement up. All right, so we'll do that real quick. Zap down to the bottom. How about a DD? Move back to the top. P for paste. Okay, so that should fix that. We'll verify real quick. It does. Now let's jump back in, pick up kind of where we left off. So I can make an assignment from B to S. You know, this is an assignment statement, and oh yes. So most of the time so far when we've been making an assignment to a variable, we're assigning it the value of a constant. But the syntax for an assignment statement says, oh, you can assign it the value of a constant, or you can assign it the value of a variable. So here we're taking the value that is stored in variable b. Well, I'll ask you guys, what value is stored in variable b? Good. You just have to look up. Well, previously in the program, what was assigned to variable b? Okay, here we go. So we declared variable b. Oh, it's just off the screen now, but we declared variable b just up there. We made an assignment to it here, so b has that value stored in it. You know, we haven't really talked about the details of it, but ultimately when you declare a variable, it reserves some memory for that variable of the appropriate size, and it associates that name with that memory location. And we can put things into it, and we take things out. You know, now what if I was to do the following? So my question for you guys, does variable b have a 1, a 7, or both? And I wouldn't expect you to know if you've not done any programming. But to be clear, a variable can store one value. And so the second assignment statement just clobbers the first one then, okay? So for this little period of time, hey, all right, we just stuck a 1 in variable b. Uh-oh, now we stuck a 7 there. The 1 gets knocked out, so not both there, just the most recent one. And again, the code executes from top to bottom, and that's how you determine which one is most recent. So at this point, variable b has a 7 in it. Okay, fine. So here, variable b has a 7 in it, so we're assigning a 7 to s. And I believe that should work just fine. We'll verify here with a quick cat. There we go. And compile. And then compile just fine. But then things will get kind of weird. Finally, we're going to pick up a syntax error here. What if I just reverse this? B is equal to S. And this is where things get a little weird and a little perhaps aggravating for new users, you know. But so these are all just integer data types, and we recognize that even the smallest integer data type, the byte, it can store numbers up to 127. Up to 127. And okay, well, B has a 7 in it. And then I assign that 7 to S. So now S has a 7 in it. And so what am I trying to assign back to B? A 7. So as smart people that you guys are, you recognize B has a 7 here. Now S has a 7. Now I'm assigning B a 7 again. So the old 7, we can say, gets clobbered, and we stick a new 7 on top of it, if you will. But, okay, so we're making an assignment to variable B, and we're assigning it a 7. We're assigning it a 7. There shouldn't be any problem there, right? And we cat, and we compile. What the heck? All right. So aggravating experience number 1 here. So again, you know, we recognize that this little variable b, it's just a byte. It's the smallest of the integer types. See, it's only 1 byte. S is 2 bytes. But the numbers that we're playing with are so small it doesn't matter. They're all less than 127. So it shouldn't matter. But still we get this incompatible types. Now to be clear, S and B are not the same type. We assign from B to S, no problem. From B to S worked, but from S to B didn't. It has to do with the data types. And once again, we have to remember that number 1 rule of computer programming. Computers are. All right, so they're just smart enough, but we can see holes in their understanding of things. So what happens here when we're assigning from one variable to another? It just uses some very simple, some very dumb little rules. And it's kind of sort of like, imagine you're going to move from one apartment to another, or from a house to another, or something else like that. And you call the moving company, And you say, hey, I've got a 2-bedroom house, but we're upgrading. I'm going to have a 4-bedroom house, and you need to come move me. They say, oh, that's great. And, you know, done. But then, you know, later on, the kids are grown and gone or whatever else, and you call that same moving company back. You say, hey, I've got a 4-bedroom house, and we're moving into a 1-bedroom apartment because we're going to buy an RV and travel for a while. We're just going to cram our crap into an apartment or whatever. And they might say, nope, can't do it. You can't put a 4-bedroom house worth of stuff into a 1-bedroom apartment. Can't be done. Well, maybe it can't be done, and maybe it can. Depends on what kind of a garage sale you had first and so on. That's exactly what the compiler is doing. The compiler allowed this because this is a 2-byte, a 16-bit variable. This is a 1-byte, an 8-bit variable. To assign from a small variable to a big variable, it says, hey, you got room to spare. You got room to spare. On the other hand, here, we're assigning from a 2-byte, 16-bit variable to a 1-byte, 8-bit variable. So we're going from a medium-sized variable to a small variable. And the compiler says it might not fit. It might not fit. That's what this error message is. Now we know that it will fit because variable s at this point in time has the 7 in it. And a 7 will fit in in a byte. A byte can store up to 127. But, you know, once again, you can see even right here, you are smarter than the compiler. All right? And we just have to recognize yes, right, celebrating. The compiler compiles the program. It doesn't execute the program. There's 2 different steps. I mean, you know that. You type Java-C to compile the program, and then at a later point in time, if you want to, you type Java to run the program, to execute it. They're 2 separate things. And we know at this point in time that variable s has a 7 because we in our mind are executing the code. B has a 1, now B has a 7. I'm assigning B, which is a 7, to S, so now S has a 7. At this point in time, S has a 7. A 7 should fit into that variable B with room to spare. We know that because we're executing the code in our mind. But anyway, the compiler, it's just compiling it, and it uses these simple rules. You can't put a big variable into a little variable. Now, there's a fix for that. There's a fix for that. Oh, we'll show you that, in fact, now. Now's as good a time as any. So, okay. So back in we go, and the fix for that is something called a typecast. In fact, we'll go to our notes and let's define a typecast. All right. A typecast can be used to tell the compiler and also also the runtime. I'll put in parentheses, and the runtime, you know, also to treat a variable, I'm just going to say a value, as if it was the specified type. Okay. I'll let you write that down, and then we'll give you a little more, and then we'll kind of explain it, and then finally we'll give an example, and it'll kind of all become clear. So we're going to use a typecast to tell the compiler in the runtime, hey, treat this value. Now, maybe the value is a constant, a variable, or an expression. Treat it as if it was the specified type. A little more detail. In our code, the typecast tells the compiler to treat the thing to its right as if it were the specified type. The typecast can be used for 2 things. Number 1, allow our program to compile. When this happens, we're telling the compiler, trust me, I know what I'm doing. All right. And then number 2, to convert from one type to another within limits. All right, I'm going to stop here and let y'all catch up with that. So we're giving you several, gosh, about the looks like 5 sentences worth of description on this bizarre thing called a typecast. And we'll use it occasionally then today to fix some problems. And it's fine, you know, it's a tiny bit of work, but there's some ways that you can kind of avoid the whole problem, and we'll show you those things then too. All right. All right, looks like the scribbling is not almost done, not quite. Boy, larger than usual number of students this class writing your notes into tablets, which whatever works, that sounds good. My handwriting, gosh, and I'm not the only one. I can't be the only one, especially these days. Good heavens! In fact, I'll ask: did all of y'all even learn cursive to write cursive handwriting? Yeah, and there you go. Y'all are kind of on the dividing line. As I understand it, at some point years ago, they kind of just quit, and so we just teach how to print, and that's it. You know, so my cursive is horrific, and my printing is not much better. And I think it's just from a lifetime of writing, not that much. If I have to take notes or whatever else like that, and at work, I'm almost always using a typewriter instead of pencil or pen, and so a tablet and a stylus and so on wouldn't work very well for me because my handwriting is just so bad these days. But all right, so let's jump in here then. So again, for at least initially, for the most part, what we're going to use a typecast to, it's to tell the compiler, trust me, I know what I'm doing. And that is the exact situation we have here. We recognize that at this point in time, variable s has just the number 7 stored in it. It has that value stored in it. And a 7 can certainly fit into our variable b, which is a byte. So we need to tell a compiler to, all right, we're going to throw in our typecast. And anyway, here is the typecast. So you specify a data type inside of parentheses. So this here that is highlighted in black, that is the typecast. That is the typecast. So the typecast is a data type inside of parentheses. And we saw in our notes that the typecast then tells the compiler to treat the thing to its right as if it were the specified type. So treat variable s as if it were a byte. Oh, now we're good. We're assigning from one byte to another byte. Now we don't have that possible loss of precision. You're looking at that error message again. We can just kind of explain what it's saying here a little bit. Incompatible types, they are different data types. But to be clear, these are different data types here also. And that wasn't a problem. Well, it's because we're assigning from a smaller type to a bigger type. So the different data types is not necessarily a problem. It depends on the sizes of those data types. The message, it's not as good as it was in the previous version of the compiler. I did an operating system upgrade, well, at the last reboot, which was about 170 days ago, something like that. Good grief, what is that? That's coming on divided by 30, so that's 5 months or something like that at the end of the summer. And when I did so, upgraded the operating system, it also updated the compiler and the runtime environment. Anyway, this message changed. It used to say a possible loss of precision. And I kind of like that message a little better, a loss of precision. Instead, they talk about lossy, a lossy conversion from a short to a byte. Where do we hear the word lossy? We hear the word lossy in computers every once in a while. Just as an FYI, you go back to the earliest digital cameras that we had and so on, the earliest digital pictures that we dealt with, the oldest format, the oldest file format for digital pictures was, can anybody guess? A bitmap, a .bmp. And actually, when I am editing pictures here, note BMP file. This is a bitmap. It's a bitmap, and it's the best one that I don't get little fuzzy, weird things going on. Everything's real crisp. I mean, my writing's horrendous, of course, but look how nice and neat everything is. Even when you zoom in on it, everything has real crisp edges. if this was a JPEG, all right, if it was a JPEG, for instance, and especially when you zoom in, it's going to get very, very, very fuzzy. And even the white areas are going to have little areas of gray shadows and so on. It just looks like heck. So JPEG is horrible for doing stuff like this. So a bitmap is the oldest file format for digital pictures. And anyway, for every single pixel that camera is capable of depending on the resolution of the camera, every one of those pixels then gets stored as a piece of data in that bitmap file. And so that was the earliest digital images that we had there in bitmap format. And that was during the early days then also when we started putting things on the internet, and the internet speeds, dial-up modems and so on, were very slow. So if you had some picture of your cat and you wanted to send it to a friend or whatever, whether it's through email or by putting it on a web page or whatever, if it was a bitmap, it was a huge file that they download very slowly, it would be drawing it very slowly, rendering it from top to bottom. It takes a minute and a half to draw a stupid picture of your cat, And so anyway, pretty quickly they realized, we need to improve the file formats, and let's go ahead and optimize them where it still looks good, but where the file is much smaller. So JPEG was the first one of those that was very successful. And it kind of just uses some shorthand notation, if you will, where instead of, if I take a picture of the wall, and I've got an awful lot of pixels that are exactly like just plain old white. Bitmap's going to say, oh, I've got a white pixel, and I've got a white pixel, and I've got a white pixel, and I've got a white pixel. A JPEG is going to use some shorthand notation. Hey, I've got this many white pixels, and I can kind of compress the data by using this meta information. And then the other thing it will do is it will also really, 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 really fine details that are stored in the bitmap that are below the level that you can see them unless you zoom in on the picture. So certain little details, it's going to say, we can do away with those and people aren't going to notice. And so you lose some detail in the picture. So anyway, when you convert with different kind of image editing tools and so on, if you have a bitmap, even something simple like this, even this stinking thing, if I was to save it as a JPEG, the file would get smaller and the details would be horrible then, and it would be unpleasant to look at, literally. In fact, I ought to do that if I could do it real quickly. Save as, and an image, and give me a choice on the data type. So bitmap, no, let's do JPEG. Okay, so it's going to write it out. I'm going to go in the board here then. I'm assuming it's saved at this point. And then, all right, let's update here. And here's image. Oh, heck, I didn't see where it saved the dang thing. Don't make me do this again. Let's see here. I would have thought it saved it in the current directory, but I didn't see it. Let's look. Save image. Pictures. Yeah, dadgummit. I wanted my current directory. So, okay, I can just pull up in pictures then. Okay, so we'll get rid of this. We'll come over here. And pictures. There it is. And actually, this is not bad. This is not bad. I'll give them credit. A lot of times you'll see little bits of gray stuff floating around. The edges get fuzzier and so on. So this did a good job of saving it even as a JPEG. The more you edit it, it will get worse. Kind of have to trust me on it. But anyway, this file is much smaller. And the same thing with movie formats and so on. There's different formats. Some are smaller than others. But bottom line is, I'll close this out, is this error message, a lossy conversion. We will lose detail going from a bitmap to a JPEG and so on. And anyway, so that is said to be a lossy conversion. Well, they invented a new word to describe that. You're losing some detail, if you will. Anyway, so that's the error message that we have here. And it's not the best, but worked okay. All right, so let's see, is our typecast going to fix that then for us? So we will cat and compile. Didn't compile before. Now it does. Okay, so back in we go. And let's play around again with good old variable b. How about if I come down here, b is equal to 127. Would you expect that to compile?
Yes.
We would. And then I'm going to assign it another value. B is equal to 128. Would we expect that to compile? No. And so the question is the compiler going to bother to actually look at the number and see if it's within range and so on, Well, we'll find that out real quick here. We'll cat and compile. All right, there you go. So, it ain't going to work. Now, and if we were to try to do a typecast, it would force it to work, but you can't store the number 128 in an 8-bit int. And so what's going to happen is you're going to lose that high order bit, and the number that you get when you print the darn thing out is going to be much smaller. In fact, it probably would, now that I think about it, probably would print a 0 when you print the thing out, or a -1, one or the other, because of we have a sign bit thrown into the mix then also. So typecast would allow it to compile, but there's no way in heck you cannot store the number 128, so you wouldn't get the results that you want. What about, back in we go. All right, oops, we need to comment this out. That didn't work. And it is kind of interesting that Java will even do a little bit. You know, I say this is the compiler, it's not the runtime, so it's not going to look up in the code and see what value does this variable have and different things like that. But it will do a little bit of evaluating expressions as long as they only involve constants. 120 plus 1, 2, 3, 4, 5, 6, 7. I think that's 7. 1, 2, 3, 4, 5. That's 7 ones I've added in. So that is 127. And anyway, that's going to work also. We'll verify that real quick. We'll cat for good luck and compile. And anyway, so this is an expression, but note that it is an expression that only involves constants. And so the question is, did it actually add those stinking things up? Well, what we're going to do here is do a y and a p and stick one more +1 on the end. So this here is 127. This here is 128. And is the compiler going to figure that out? Let's look and see. We will cat and compile. And isn't that interesting? All right. Possible lossy conversion. And anyway, so it allowed the first one, but not the second one, because sure enough, the sum of all of these constants is 120, and it did add it up. That's kind of surprising. But as soon as you throw a variable into the mix, then things get kind of weird still. So, okay, we'll go in. Don't forget to comment this one out. All right, so how about this? B is equal to 0. B is equal to B. This is really weird. This is the worst case example here, I think, of something that's not going to work. That certainly, we can make the point that it should, but we just have to show you what works and what doesn't, so you'll know to avoid it and how to fix it and those kind of things. All right. So we've been playing around a lot with B just because it's a very nice little, very small integer data type, and it's very easy to give it values that are too big. But in this case, B is equal to 0. So when this line of code is executed, this expression here is going to be B, which is 0, plus 0, the sum is going to be 0. You and I know this should work. That this should work. We got plenty of room in variable B to assign it the sum of 0 plus 0. And yet, this is almost embarrassing. All right, this is almost embarrassing how clueless the compiler is. But again, it's compiling, it's not executing. So it is strange. It's just, but you just have to learn what works and what doesn't. Here on the assignment statement itself, it will evaluate this expression if it involves only constants. But here, it's not going to evaluate this expression because it's not going to look up, back in time, if you will, and try to figure out what the heck B was. That takes place at runtime, not at compile time. So it doesn't know what B is. So we have variable B, plus we're trying to add some integer constant to it. See, check this out. A lossy conversion from int to byte, right? My variable is a byte. Where's the int? Well, it thinks that this expression is an int expression. An int expression. Not an integer, but an int. Now, isn't this weird? These are all integers, but it looked at them and it could see how big they were and so on, and it added them together. Oh, that's 127, we're good. But when it evaluates this expression here, it says, well, this is a variable of unknown value, and then it just defaults and it thinks this is an int constant. And if I add an int constant to a byte, well, then I need 4 bytes in order to store that result, and that's where this int comes from. So isn't that weird? So can we fix that with a typecast? Yeah, but we have to make sure and read my instructions here very clearly. So let's minimize that. We'll bring this back and then click this up on top of it, kind of like we were earlier. So we'll fix it with a typecast. So this may or may, tell you what I'm going to do here, just for grins. I'll come up here. and I'll comment out the previous one without the typecast that didn't work. So anything that's commented out doesn't work. So now the question is this going to work? We're throwing in a typecast, but we're not quite doing it right. So let's look here why, and we'll figure it out, then you'll understand. So we're going to cat, compile, or well, try to compile. We still get the same error. Okay, so we have to look at, this is very bizarre, we have to look at my notes. When I typed the thing, you probably thought, oh, good grief. That's as precise as this old guy could be. The thing to its right. All right, the thing to its right. The thing to its right might be a constant. It might be a variable. It might be an expression. I guess I could have said the value to the right. But anyway, let's take this, the thing to the right. So my question for you guys is, what is it that is immediately to the right of my typecast? Variable b. B is already a byte. B is already a byte. Typecasting a byte to a byte does nothing. It's not variable b that's the problem. It's the value of this expression, which is the problem. It's the value of the expression. We take variable b and we're adding again, the compiler. We see from the message, the compiler thinks that 0 is a 32-bit int constant. That's a weird concept. We have variables that have sizes associated with them, but sometimes constants kind of have sizes associated with them then also. So it thinks that this expression is an int. The int part doesn't come from b, it comes from adding a byte with this constant, and it just has decided that that might be a 32-bit constant, and that's why we get this particular message. So it's the result of this expression which need to be typecast. How might we fix that? Kind of like in algebra, when in doubt, sprinkle in some parentheses. Okay, so just like in math class then, so kind of do me first here, if you will. So, all right, so now, because of the parentheses, this expression is being typecast to a byte instead of variable b being typecast to a byte. Oh, yeah, and just to be consistent with what I did before, let's go and comment out the one that didn't work. So it didn't work. This typecast didn't work because it was just typecasting variable b. I'll put a note here. Typecasts, casts. All right, variable b. That didn't work. Here we are typecasting the expression. All right. Let's see if that works. Okay, we will cat and compile, and it works just fine. Okay, so there's that. And so moving on, down we go with a capital G. Is a good way to skip down to the bottom of the file if you remember that in DI. And, what about this here? So B equals B plus 0 didn't work. Good heavens. But what about this? Would you expect this to work? If you remember, it didn't like this expression here because, well, it had a variable, and then when it looked at this constant, we recognized that for some reason it just assumed this was a 32-bit constant. And we're going to add a small variable and a big constant. Well, I need room for the big one, so it assumed that that expression was going to be an int value then for the expression. Same thing here. I'm adding an int variable, and it's going to assume this is an int constant, so that sum is going to be an int. But, I'm assigning it to an int. So the good news is the thing that causes a problem with our variable byte is no problem at all with int. Okay. Now you could get we would get the exact same problem if we came through here and we changed this and this and this and this to short. We still have the same problem. A short is 2 bytes, but that's not big enough to store a 4-byte quantity. So we'd have that problem with byte or short. Int, on the other hand, finally we found one that works without making us unnecessarily add in the complexity of a typecast and the extra parentheses and everything else. So that being the case, okay, we're going to come up here and next to int, I'm going to put a star. Okay, this is our preferred int. Our go-to, if you will, integer data type. So, if we were writing the lunar lander code for the lunar lander in Apollo 11, and they had a computer that had 32K of RAM, and we're writing assembly code, we're very limited on memory, and if we had a very small quantity we need to represent as an integer, we'd put it in a byte, all right, not waste memory by having it take up 4 bytes or more or something else like that. But well, that was 50 years ago. We're not doing that, and now memory is cheap and plentiful. So for the most part in this class, and PF2 also, we will often be lazy. And if I'm dealing with an integer and it's still going to have small values, because of the problems we've just seen, I'm not going to use byte or short generally. Instead, I'll use int instead. Now, so I guess the question comes up, well, why do we even need byte or short? Well, sometimes you might have your program interact with hardware or with other programs over the network or something else like that, and we need to format some data just so. And if the specification says, pass me a 16-bit int or an 8-bit int, then we're going to do it by using our short or our byte data type. But short of that, we're going to use int. It is our favorite integer data type. So with that in mind, let's then go down and do a little bit of quick experimenting with our floating point data. So how about, and gosh, I think it's kind of just as bad on the floating point side of things. So f is my 32-bit floating point variable. F is equal to, now if I was to do something like this, 3.14, a very abbreviated version of pi here, if you will. And I got 32 bits. Now part of that is going to be to the left of the decimal point. Part of that's going to be to the right of the decimal point. And we can talk more about that later. But still you'd think, that's still a pretty small little number. Surely I ought to be able to store that in a 32-bit int, 32-bit float. We will cat and compile or try to compile. And would you look at that? Oh, here we get a good clue. All right, can't convert a possible glossy conversion to a float from a double. Well, here's the float, f, the double. So anyway, once again, sometimes Java is going to associate a size, a data type, if you will, with a constant, just like we do with variables. And Java thinks that 3.14 is a floating point constant, or excuse me, is a double constant, I should say. If we go back in, and this is really kind of silly. In fact, I don't know if I've ever taken it to the extreme. If I make that a 0, 1.0, it can't take a whole lot to the left or right of the decimal point to represent 1.0, surely. But, isn't that crazy? So anyway, so that kind of stinks. A couple of ways to fix that. So we'll go in and comment this out, and we'll show you 2 ways to fix that then. All right. So I'm going to do a YY and a P. And this one didn't work, so we'll leave him there, but comment him out. This one we're going to fix him 2 different ways. We could, all right, float. There's our typecast. Treat the thing to the right, that floating point constant. Assume that it is a 32-bit float instead of a 64-bit double like you are apparently doing, and that should fix it. So we will cat and compile, and it did fix it. And there's another option, which is to come down here. We'll do a YY and a P, and with floating point constants, another option is you come to the end and you can type actually a lowercase or uppercase. Either one will work. I always use uppercase. It kind of stands out a little more. So you stick an uppercase F on the end, and that's just a way to tell the compiler, hey, this constant, it's a floating point constant. It is a float constant, I guess I should say. And we'll see if that works for you too then, in case you're still typing. Oops, it did compile. We'll cat real quick. So that worked also. But the bottom line is, let's jump back in and show you, okay, those worked, and both of them a little bit of a nuisance. Really, the nuisance isn't typing in the typecast or typing in the capital F. The nuisance is you'll forget to do it, then you'll get a compiler error, then you'll grumble and go back in and fix it. But on the other hand, double D, oh, that's right, I already declared D, so a D is equal to whatever. And there's all the digits of pi that I've bothered to memorize. Let's see if we're going to have any problems with variable D, our 64-bit double. And the answer is no problem. Back to the notes we go. All right, I'll be lazy and steal this. Control C, come down over here. Control V, oh, need to do a little tab there. Okay, about like so. Our go-to floating point data type. And I'm going to put my star up here to the left of double. There's that. Okay. All right, we'll move pretty quickly through our other data types just to show you examples of those then. let's move on to Boolean. Okay, so Boolean, sometimes I'll have it BOO. If we're teaching this lesson in the fall, it might be BOO in anticipation of Halloween, but we've just got a BO. So let's make some assignments to variable BO. BO is equal to, now we'll try a number of these. They can store the answers to yes, no, on, off, true, false kind of questions. So how about yes? And BO is equal to on, maybe. And BO is equal to true. Well, yeah, it kind of can store the answer to yes, no, on, off, true, false kind of questions. But actually, only one of these is actually going to be understood by the compiler, the yes, on, or true. The compiler will understand true, but not yes or on. So, all right, so... all right, we get a compiler error on the line of code with a yes and a compiler error with a line of code with the on. So yeah, ultimately, even if it stores yes, no information, we'll have to represent it in our program with true or false. So we'll comment this out. Comment it out here. That didn't work also. And just to be thorough, the nice thing about Boolean, oops, true. How about false? There we go. Nice thing about Boolean variables, Boolean arithmetic, and so on, is, you know, in the world of integers, if you make some claim about, you know, some operation in the world of integers, there's any number of different ways you have to prove that, and it's kind of an involved process because there are an infinite number of integers. An infinite number of integers. On the other hand, if you're dealing with Booleans, the number of constants in the world of Booleans, 2 of them. Just those 2. So you can use what are called truth tables and so on, and you can prove things just exhaustively. Well, here's the only possible values this variable can have, and you plug it into your expression anyway. It's much easier to prove things in a world of Boolean where you have 2 constants instead of the world of integers where you have an infinite number of constants then. But anyway, this is it. Those 2 are the only 2 Boolean constants, and we'll cat and compile, and that should work just fine. Let's jump back in. And also, hey, what about, and we're going to jump into operators later. Oops, I got caps lock on me. By the way, if things ever start acting really, really weird in VI and things aren't working right and so on, look down to see if you got your caps lock light on. If you accidentally hit caps lock, it will mess you up. And we can come down here. We're going to talk about operators. Is it the next lesson, or it might be the lesson after? I think it might actually be the lesson after this one. But I'm going to go and just sneak in a relational operator that you guys are well familiar with here that we can use to create a Boolean expression. You know, like up here, hey, this is an integer expression. What's a Boolean expression look like? How about, you know, B0 is equal to, and we'll say 2 or 3 is less than 4. And actually, now that I say that, the parentheses aren't necessary, so I'll leave them off. There we go. So this is a relational operator, the less than that we're familiar with from math class. Okay, is 3 less than 4? It is. So the result of that expression is true. It is true. So this is just an alternate way to assign our Boolean variable the value of true by using an expression. All right, so we will cat and compile. Looks good. Moving on from Boolean. Well, we've got characters and strings, I think, is all we have left at this point. We'll knock those out fairly quickly. Now, let's just show you some things that will work and some things that won't with character variables and character constants and so on. All right. That is good. And that is good. And this is good. And all right, I'm doing a lot of YY and then P. And, you know, we could use special symbols, you know, and different operators and whatnot, you know. All right. Those are all perfectly fine. Those are character constants. You know, this up here is a floating point constant. This is a floating point constant. We've seen integer constants and Boolean constants. These are character constants. Character constants appear between single quote marks. So this will all compile, and then we'll show you some things that won't compile. So we will cat, in case you're still typing, and compile, and run. Oh, I did compile. There you go. That's right. We don't need to run. I don't have a single print statement in here. So it did compile. Let's jump back in and show you some things that will not compile then. How about if I come down here and say C is equal to... Well, that compiled earlier. I used single quotes then versus double quotes now. Surely that doesn't make a difference. It does make a difference. To be clear, These are character constants, and this is a string constant. Strings, oh yeah, that's our other data type down over here. And anyway, there's a difference between a character constant and a string constant, and just the whether you're using single quotes or double quotes makes a critical difference there. So we'll cat and compile, or we'll try to compile, and it can't convert from a string to a char or to a character. That didn't work. So back into VI we go. Oops, back into VI we go. Down at the bottom, we'll comment him out. And to be clear, character constants have to be just a single character long. And oh yeah, I need to go up here and put some more in. For instance, that I did. Oh, I think that's a 0. To be clear, let's throw in some others. You can put numbers inside character constants, perfectly fine. All right, but what you can't do is like the following. Well, this is 2 characters. Character 1, then the character 2, if you will. And it wants a single character. A single character. That ain't going to work. This ain't going to work with no characters. All right, so there's examples of things that won't work. All right, so let's verify that. We'll cat for good luck and compile. Try to compile. And sure enough, 12 didn't work, and here the empty closed literal, it didn't like that one there either. So you have to put one. It could be a letter of the alphabet, it could be a number, it can be a piece of punctuation, special symbols, and so on, but it can't be nothing, and it can't be more than a single character or number or whatever. Okay, so we're going to go back in and comment those out, and then we'll move on to strings, and we'll wrap this up here pretty quick. All right. How about, now, I was going to say S, but I think it's ST. Am I remembering that right? ST is my string variable. So, all right, ST is equal to hello world. Hey, we'll let that string rear its head here. How about ST is equal to, that is perfectly fine. ST is equal to, that is perfectly fine. Oops, I forgot my semicolons on those. There we go. There we go. And moving on, ST is equal to, this is perfectly fine also. And so on. All right. So strings are ultimately very flexible. You can stick just about anything into a string. The question is, once you get it into that string, what can you do with it? Well, you can print it out. And anything beyond that, it doesn't work very well. You have to figure out how to get whatever it was out of it. So, we can store what appear to be integer constants, the number 15 here. To be clear, yeah, it looks like an integer constant, but because of the double quotes, this is a string constant. It's a string constant that stores, the character 1 and the character 5. They're not numbers, if you will. They're just characters in a string. Same thing here. Looks an awful lot like the shortened version of pi, but that's just a sequence of characters inside a string constant. Same thing here. And, oh, that looks like a single quote. Oh, that was a typo here. Make that a double also. So this will work perfectly fine. You can store, a single character in a string, but you have to store it as a string constant, not as a character constant. Boolean constant, well, you can stick the word true as a word, if you will, as a string into a string. So these should all compile. Here, this looks like an expression, but, well, it's just a sequence of characters, a 3 and a space, and a less than and a space, and so on. So these should all work just fine. So we'll show you that the string is very, very flexible. You can stick anything in it. Oops. That must have been a typo there. What happened there? 15. Oh, okay. That was copy and paste here, it looks like. Go back up. That was line 78. Colon 78. Get rid of that 15. Oh, yeah, okay. I don't know what happened there. I must have fat-fingered something with VI. Oh, I wanted a 15. I already got it, and it's down there. I guess we're good here then. Just needed to delete that line. I was doing some copying and pasting earlier, and it got out of hand, it looks like. We'll cat. Try again. Compile. There you go. So, hey, to be clear, while I say that, an interesting little development, I guess. The midterm test is going to change a bit, but still, on the midterm test for you guys, you will need to declare some variables of the appropriate type to represent, a kind of a word problem that's described. So kind of expect that. We'll talk about it more as we go, as we start writing programs, but for instance, if I was to have you write a little program that could keep track, the silly little example I always use, if we're going to write a little program to keep track of the number of cars in the back parking lot, all right? Well, we go to the window and we can count, and I've done it one time before. I don't remember exactly what the number was, but it was double digit. It was a double digit number for the number of cars that can fit in the back parking lot. So if it's a double digit number, then we recognize that, hey, that's going to be an integer quantity. I mean, we can look out the back window all day long. We're not going to see any half cars driving through the parking lot, right? So the number of cars is going to be an integer quantity. And the truth is, since it maxes out at 99 or something like that is the number of parking spaces we have out back, we can store the number of cars in a byte or a short or an int or a long, any of those. And in fact, on the test, any of those would be a perfectly fine answer then also. But I'm going to say it's perfectly fine to use good old int for all of your integer needs. Just feel fine to just use int. But we would want to use, if we're representing that quantity of the number of cars in the back parking lot, maybe we're writing a program to kind of keep track of that as the cars come and go, and we're incrementing and decrementing as cars are pulling into the lot, next to the lot, and so on. We would want to do arithmetic with that variable, so we would need it in an int variable, or an integer variable, not, for instance, as a string. But so being able to recognize the appropriate data type. If I ask you to write a program that would deal with your bank statement or something else like that, well, financial quantities, you have dollars and you have cents, and so you would want a floating point variable, either float or double or something else like that. What would be the appropriate data type to store your name? String, exactly right, Ruben. What about your middle initial? Character would be good, yeah. And to be clear, all of those things could be put into a string, but string would not be the best answer. Again, especially if we're assuming we're doing some calculations or something like that, we would want to, where applicable, use the integer types and the floating point types and those kind of things. So string's very flexible, but for the most part, we don't want to store numbers inside of strings because we can't do arithmetic on integers or floating point numbers that have been stuck into a string. We would have to jump through a couple of hoops to get them out of the string and stick them into an appropriate variable. But anyway, so being able to recognize what would be the best of our handful of data types to use to store certain quantities is something that we'll kind of practice on and that you'll need to then be able to demonstrate on our midterm exam coming up here in, well, about, I was going to say 4 weeks, but to be clear, normally we have the exam after the fall or the spring break so that I'm not giving the midterm exam on the exact same date when you guys are having final exams in your 8-week classes. So anyway, do plan on having your midterm exam as soon as we come back from our break, from our mid-semester break. Whether, again, if you're listening to this video, it might be spring break, it might be fall break, either one, but that's when we'll have our midterm. All right, so we covered today data types, assignment statements, verbal declarations, and quite some, perhaps too much excruciating detail, but you're starting to become experts on that. We can use typecast to fix some problems here and there also then. Questions on any of that? No homework today. And I'm trying to remember, I think, if I remember correctly, I think that we introduced Lab 2 in the next class, the next video then. So none until then. We'll see you then in the next class period. Then you have a good couple days.